All right, in this module, I want to start talking about the contrast that we can generate in TEM in imaging modes. So I want to start with a comparison to what we've already talked about. So we've talked about light microscopy, and particularly transmission light microscopy, which compares the best to TEM. And in that case, we had differences in contrast from differences in the way that light is absorbed in different regions. So if we take this image here, then the light regions absorb less light, and so they appear light and bright field mode, whereas these other ones, like these sort of particles or grain boundaries, absorb more light and appear dark in bright field imaging. And so there's a reduction in the amplitude as kind of shown in this schematic here. So that's what gives us differences, scattering or absorption of light. TEM is not generated by this type of absorption of light. Instead, we're dealing with electrons, and the main part here is electron scattering. That is the principal generation of contrast in TEM. So if we kind of think about it from the schematic here, we have the primary beam and the sample that's transmitted through. It goes through the objective lens and onto that fluorescent screen that we talked about. So scattering of that beam by the specimen then causes electrons to effectively deviate from that pathway that we see here. And so that would result in this case, that scattered beam hitting the aperture instead of passing through the opening. And so areas where there was scattering, less light makes it through because it's hitting the aperture, and so that appears dark down here. So this region up here corresponds to this region down here. And the regions where there wasn't scattering, more light passes through, less is scattered onto the back of the aperture, and so we have a bright image in that case. So this gives us the main contrast in TEM that we'll talk about. Okay, so with that in mind, here's our quiz question for this. What causes electrons to scatter differently in a specimen? So think about a specimen and things within that specimen that could cause the scattering of electrons differently within that. Answer the question, pause the video, and then come back and we will discuss. All right, so now that you've had a chance to come up with some ideas of how electrons scatter differently in a specimen, let's go through some of those options. All right, so the first one I want to talk about is what we call mass density contrast. So this is the mechanism in which the electrons are deflected when there is more mass present. So we have a couple options here. So obviously this could be due to a thickness difference. A thinner sample would have less mass. It could also be due to density. If there's different densities in the material, the more dense has more mass, and so that would cause differences in scattering. But it's all kind of connected to the same type of contrast mode. And so in these, the deflections of the electrons, because of this mass density contrast, are a result of interaction with the nucleus of the atom. So that's kind of what's actually causing the deflection. So again, thinner, less dense regions. So again, it can be, there's a couple different things, thinner, but also less dense. So you could be talking about a difference in phase or a difference in thickness. There's options here. And so in this sample here, there appears to be a thin region here in this part, but there can also be less dense regions as well. There appears to be multiple phases, and so the light regions will appear lighter as well. So in this way, this is like bright field. This is bright field, but this because this is bright field, the things that deflect or scatter less appear bright because more of the electrons are reaching the screen or the detector, and then thicker, more dense regions such as the regions here, and then again on these images as well over here. Those have more mass because they're either thicker or denser, and so those deflect electrons. And this is an error here. It should say more. And so they deflect more. And if you think back to this image here, they're scattering onto the back of the aperture. And so less make it to this point. So again, the error here, this should say more. All right, so about this mass density contrast, we are going to see different mechanisms for contrast in TEM, but this one is particularly important when we're looking at amorphous materials. So you could probably think of quite a few types of amorphous materials, glasses and so forth, but also polymers. A lot of polymers are amorphous, and also biological samples tend to be amorphous. And so this is really the only mechanism we have of contrast. And so, these images that you see here of these liposomes or this piece of rubber, these are because of that mass density. So a part is either thinner or thicker, or it has more or less density. And so that's the contrast that we get. And so the contrast that we get often tends to be weak in these cases. And so a lot of times, and you see it here, is that these samples often have to be stained. So this one is stained with osmium in order to enhance the contrast. So the idea being that the stain will interact with certain regions, and because you have something like osmium, which is very dense, then that will give you that added mass density contrast. So that's an issue with amorphous materials, is that we have this mass density contrast, but it's our only mechanism. We're going to look at some other ways in which we can get contrast, but it relies on crystallinity and structure. Okay. So that brings us to the next type. So along with mass density, we can also have contrast from diffraction. So we've talked extensively about diffraction in the context of Bragg's law, as we've mentioned on several occasions. And so this is, in this case, instead of X-rays, we have electrons. And so the idea here is that these electrons are collectively diffracted in accordance with Bragg's law, and therefore that's causing the electron scattering that we talked about in the opening. And so this kind of emphasizes what's happening there. Is we have a crystalline material here, which is our sample. Our incident beam, electron beam, is coming down, and then if it's at the right angle, it will diffract by that angle theta, and that will cause those collective electrons to diffract and again hit kind of that back portion of the objective aperture instead of going through. And so that diffraction reduces the intensity of the incident beam when the objective aperture blocks these diffracted beams. And so in this case, in this type of mode, again, what's the transmitted beam is what makes it through. The diffracted is not. It hits the back of the objective aperture. And so that kind of if this is the thin strip that is crystalline, then that appears darker in the image. So But as you would expect, diffraction contrast would only be possible with crystalline solids. So those polymers and those biological samples that are amorphous, this would not give us that type of contrast. And so that's why we only have mass density. All right, so diffraction contrast obviously relies on Bragg's law, and so we have the incident beam is like our X-ray beam from XRD, and we know angle is very important there, right? Because we have to have the alignment such that we are in a certain Bragg angle such that we have diffraction. In other orientations, we tend to not have that constructive interference and therefore diffraction. So the angle of things, the orientation is very important. So this is why I briefly mentioned those tilt holders on TEM, is because sample tilting and orientation is highly dependent on the type of contrast we get in this mode. So, again, this is an image looking at a sample with crystalline it's crystalline, but it also contains a crystalline object or an inclusion, and so the angle of that inclusion will obviously either cause it to diffract or not diffract. And so this is an example of some what's called nanocubes. So they're nanoparticles of a certain material that are in a cube shape, and they tend to grow in different crystallographic directions and planes. And so the ones that are dark here are those that are at the right orientation with respect to the electron beam, such that they satisfy the Bragg condition from Bragg's law, and therefore appear dark. So you can see these, all these dark ones have, you can assume, are diffracting because they are at the right orientation. However, you can also tilt that sample, and in doing so, different crystals would be at different orientations. And so you can see that these same crystals over here that correspond to these are now light, and these other ones are dark. And therefore different ones are diffracting now than others, because essentially we've tilted the sample. And so again, tilting is very important. Orientation goes along with that. So for these types of studies, those double tilt holders, which allow a lot more rotation of the sample, are very important if we want to utilize diffraction contrast. All right, so let's look at the next quiz question I have for you. And that is, if we're talking about this diffraction contrast, there's going to be a specific scattering angle with these materials. So let's say that we have a typical interplanar spacing. So we're just using a generic 0.2 nanometers as our interplanar spacing. And then I've given you the, instead of the copper K alpha or whatever our X-ray wavelength would be, I've given you the electron wavelength. And so see if you can figure out what a typical scattering angle in accordance with Bragg's law would be for this type of despacing using these types of wavelengths in TEM. So make it that quick calculation, stop the video, and then come back and we'll see if we arrived at the same place. All right, so now that you've had a chance to calculate the scattering angle for TEM, let's take a look at our work. So we've got Bragg's law. Bragg's law doesn't change, so we use that as well, and rearrange it if we want to solve for the angle. And so it's sine inverse of lambda over 2d. Again, d is the interplanar spacing, and so this is what we're approximating to be 0.2 nanometers. And then the wavelength you can find from the table of electron wavelength, but you do need to know that it is at 20 kV, the accelerating voltage of the beam. So putting those numbers in, again, importance of units, so make sure that these are consistent, and the angle of this scattering event will be at 0.36 degrees. And so this is important, and I wanted you to have a reference point here, because when we did XRD with those wavelengths and d-spacings, those were, in the range of like 10 to 100 degrees, the predominant scattering angles that we saw. Here, the angles are much smaller, right? And so this is indicative of the diffraction angles in TEM being very small. And so when I say small, we're talking about on the order of 0 to 1 degrees, right? So we're not talking about these huge scattering angles. We're talking about very subtle. And so when you see the schematics and you see these, we can go back and look at this, right? So we see these huge, differences between the diffracted beam and the incident beam. Remember, we're, talking about angles that are around 1 degree or less. So that's important to keep in mind when we start looking at diffraction.